What's up, YouTube? Mud Duck Sharky, and if you've read the title of this video, you know we're going to be messing with some LDMOS. So this is basically the first LDMOS amp I've completed. It's really not the first. I was running one for a while. It was actually much cooler looking than this ICA case, but I decided to forget about that project and go with this one. So, this is a single MRFX 1K80H LDMOS device running at 63 volts. So I guess where do we start? Let's start on the back of this thing. So this wire right here, this is just to switch over the relays. It's connected over to the radio. We've got our 63 volts coming in through here, which is coming from an ESP 120 power supply. This has been modified up to 63 volts. That's pretty much all you can get because the output capacitors are 63 volt capacitors. Over here we got the input from our radio, and this is our output. So this output is going through this bird meter, the 5K slug, and then out over to the dummy load through the line section with the sampler slug, and that sampler slug is coming over here to the oscilloscope. You may have noticed these attenuators here. So this is pretty cool. So if you want to run a bigger radio into this or a smaller radio, you can change the attenuator that goes in between your radio and your LDMOS. Attenuators are mandatory for LDMOS for reasons I'll explain in a minute. But yeah, these are the connections for the attenuator. So when you're receiving, it's just directly connected from output to input, and your antenna signal comes in over to your radio. But when you transmit, the signal from the radio goes in through here, comes out through this top port, back in this way through the attenuator and into the board, and that's to knock down the power of your radio, so you don't blow up these super sensitive LDMOS chips. But on the input, we've got a 10-watt slug and forward, and we're going to be using that on this meter to show how little drive it takes to get this thing running. Alright, so I'm ready to click over the buttons. Before we get started, I apologize in advance. This fan is very loud. It kind of has to be. So this is an ICA 6-pill cabinet, and the biggest heatsink that they have that'll fit in here is it's adequate, but it's a little less adequate than I'd like it to be for this LDMOS palette. So I had to make up for it with a beefy, very loud fan. So I apologize for that in advance. But I'm going to fire this up and run it, and then we'll open the lid and see what's inside later on in the video. Okay, so I got my radio going through the bird meter, or that bird meter, over to the input of the amp, coming out of the amp from that bird meter. Let's hit the button. Okay, so that's a 5K slug and forward, and that is a 400 watt dead key. Let's run that up and see what we can get. Alright, I'm going to stop there. These LDMOS are real sensitive, and I just don't like pushing my luck, man. I've got a graveyard of LDMOS chips. Oh, there's the fan. I've got a graveyard of LDMOS chips from doing stupid stuff, you know, trying to push it. Alright, let's do some modulation here. I'm going to go into peak mode, and then I'm going to add some modulation. Okay. No modulation? With modulation. Okay, so our carrier is at 400 watts, and we're modulating up to 1400 watts. So that's pretty good as far as linearity goes. Our sine wave is still very sine wave-like. You know, it's very sinusoidal. We have good linearity with these amplifiers. Let's see where we can push it though. That's a nice 2K right there. That is 2 kilowatts. You know what? 2K. Alright. So that's what she do. Let's pop open the lid and see what's inside. I just realized after watching this video, I sincerely apologize for how loud that fan is. It's really that loud in person. It's excessive, and I'm going to change it. I forgot to show you how much input power it takes. So before I do that, this is 10 dBs worth of attenuation. So I've got 1 dB, 1 dB, 3 dB, and 5 dB. That's just what I had on hand to get 10 dB. Let's take a look at input drive over here. So I got this in peak mode. So we're back up to our 2K. This is a 10 watt slug and forward. We're going to go to 2x, and we're going to put it in peak mode. So what is that? A 10 watt slug, that's 16 watts and forward. And then let's turn off our modulation and go back to our 400 watt carrier. So sorry about the fan. A little bit over 1 watt to get a 400 watt carrier. So those numbers I just showed you, 16 peak watts and 1 watt carrier. Those are going through a 10 dB attenuator, which means the amplifier is getting 1/10 of that power. So for 16 PEP watts, we're getting 1.6 PEP watts into that circuit board to get 2,000 watts out. Let that sink in. To get 400 watts, we're only putting 0.1 watts, 0.12 watts of power into that board to get 400 watts out. Let that sink in. But anyway, on to the part where we take off the lid. Alright, so this is the inside of the 1-pill LDMOS box. So, what you see in here is probably nothing too shocking. It's based off of the NXP reference palette. So this is the NXP reference palette. You can buy it directly from NXP. You plug it in, it works out of the box. It does basically the same amount of power that this one does. But I decided to build my own board with through-hole components instead of surface mount components. And I built it out of cheaper materials, and you know, building this yourself is a fraction of the price of this. This is a $1,000 pallet. This is a $400 pallet. You know, if you don't count all the time involved, the heat spreader itself, you know, takes a significant amount of time. That chunk of copper is probably, I don't know, $20, and then machine time on it. So for me to make this, it's a lot cheaper for me to make multiples. You know, I wouldn't be spending $1,000 a pallet. But yeah, so this pallet is essentially the same as this one. There's just a few very slight differences. The input tune is a little bit different. I chose a metal clad capacitor instead of an ATC capacitor for price and availability reasons. But most of the other stuff is the same. The circuitry for the bias is identical. It's just through-hole components instead. So that's the pallet. Underneath this little copper bar here is the LDMOS chip, and it looks just like this one here. These little suckers are pricey, $250 a pop. But man, they're worth it. So what we've got going on is this is our input switching relay. So when we turn on the input relay, it redirects our input signal over to the attenuator. And this relay also turns on the bias circuit for the LDMOS board. This is our output relay. So if you notice, each wire is paralleled on the relay. And that has an interesting benefit. So you notice there's no tuning capacitors on my relays anywhere. There's no tuning. That's for a good reason. That's because I used coax to go to and from the relay, and I just used good practice as far as handling radio frequencies. And the pass-through tune is like 1.1, and the output tune is even better. So if you use good practices when you're running your coax and things like that, you're not going to have to fix your pass-through tune. You're not going to have to compensate your output tune. You're not going to have to compensate your input tune. It's just, that's the way it goes. You know, you don't have big old long chunks of open wire acting like an inductor that you got to compensate out. So the reason I mentioned this output relay, you notice the connections are parallel. So this one's a dual pole relay, but each pole is being used for the same purpose. And what that does is that cuts the amount of inductance going through. If you see under this cover, there's a wire. So when your RF goes through that wire, it encountered that wire has inductance. So if you run it through 2 parallel inductances, what do you get? You get half the inductance. So that's why I didn't have to tune any of this. You know, if I plug this into a meter from the output of the palette, which is right here, to the output here, it's like 1.05 to 1. You know, just little tricks like that are pretty cool. So over here is a step-down converter that takes my 63 volts down to 12 volts for the bias circuit, the fan, and the relays. Over here is a fan speed control board. So this is a little switching fan speed control board, and it was a good idea in principle, but it when this thing runs the fan at half speed, it tends to put some RF noise into your receiver. So right now I've got it configured like an on and off switch. There's a temperature probe. Where is that temperature probe? It's around here. Yeah, that's it right there. So that's the temperature probe. It's connected directly to the heat sink. It senses that temperature and turns the fan on and off when it's needed and when it's not. But like I said, the problem with it is it's a switching. Ooh, fireworks! All right. It's a switching control, so it feeds a little bit of interference into your receiver. But that's kind of the ins and the outs of it. There's not a whole lot more to talk about here. You've already seen what it does, and I just thought I'd make a video about it because this is pretty exciting. You know, I've got the 1-pill section down. This is rock solid because I based it off the reference design, which is rock solid. So now that I've got this done, I can move on to bigger and better things. Oh, one more thing I wanted to mention. The harmonic output on this box. It's good, but it's nowhere near perfect. So if you were to go out and buy one of these palettes like I did, you're going to get fantastic performance, but the harmonics aren't going to be spectacular. You're going to have, I think it's the third harmonic is like 25 dB down, which is not great. It's not spectacular. So this box needs to be run with a low pass filter, like this one here. So thankfully, this is a 3 kilowatt, quote unquote 3 kilowatt. Who knows what it actually handles. It's a 3 kilowatt low pass filter. You can find them on eBay every once in a while for like 30 bucks. You just run it between your radio and your antenna. It has a tendency to screw up the SWR a little bit, but it keeps your signal clean. And you know, having this low pass filter, that's a 1-pill problem. So what I mean by a 1-pill problem is if you have 2 of these going in parallel, you know, you combine them together, you split the input into 2 palettes, and then you combine the output into 1 signal. You're going to have some extra circuitry. You're going to have a combiner. And there's different kinds of combiners that you can build. Some of them have inductance, and they can actually give you the benefit of reducing harmonics. So that's the next step for me, is I intend to build a 2-pill version. And then depending on how well that goes, if I blow some chips up and I can afford to keep going, you know, we'll see. I might go to a 4, I might go to an 8, you know, whatever the future holds, however bored I get and however much money I want to spend. And the cool thing about that is it's going to have a combiner, and in the combiner, I can use the combiner kind of like a low pass filter and get some of the harmonics out. But anywho, I hope you enjoyed this video. Yeah, I hope you enjoyed the video, because I enjoyed building this amp. This is fun for me. But thanks for watching, guys. I'm Mud Duck Sharky, and I'll be back again. Take care.